Here we introduce transport layer protocols for TCP/IP in support of building communication between applications. The transport layer is associated with the end-to-end behavior of transport layer protocols that are defined once data reaches the intended destination. TCP and UDP represent the protocols commonly supported within IP networks. The characteristics of data, such as sensitivity to delay and the need for reliability, often determines the protocols used at the transport layer. This section focuses on the knowledge of how such characteristics are supported through the behavior of each protocol. So upon completion of this section, it is generally expected that trainees will be able to describe the common differences between TCP and UDP, describe the forms of data to which TCP and UDP are applied, and identify well-known TCP and UDP-based port numbers. The primary responsibility of the transport layer is as a form of network management layer for IP, and is often used to ensure that packet delivery is achieved successfully. TCP is one of two protocols that are commonly found used as part of the packet delivery mechanism of the TCP/IP protocol suite. While the network layer through IP is responsible for defining the route or path that should be taken between the source and destination that may or may not be part of the same network, TCP is responsible for ensuring reliable end-to-end delivery of packets over this route. It achieves this by establishing a connection between the source and destination prior to the transmission of IP packets over the network. As a result of this behavior, TCP is considered to be connection-oriented. In the example, host A and host B are shown to establish a TCP connection over the network, allowing both end stations to be effectively in communication with one another while transmission takes place. TCP connections are communicated through port numbers. Each connection will be represented by two port numbers, one that represents the source point of the connection and one for the destination. Every application that relies on TCP will be associated with one or more port numbers. These port numbers represent a mapping to individual applications and services. For example, in the image that we see here, host A has established a connection with the HTTP server in order to retrieve HTTP files that are used to load information on a web browser. For this connection, host A has been assigned a port number of 1027, with the destination being associated with port 80. We give an example of some other common ports that are associated with common application layer protocols, including FTP, Telnet, and SMTP. Such common ports that exist in the range of 0 through to 1023 are referred to as well-known ports. Many applications may also be associated with a port range from 1024 through to 49151, known as registered ports. Ports that are assigned to hosts connecting to services in the well-known port range will generally be assigned a port number within this registered port range. We show here the TCP header as part of the packet encapsulation process and represent the information fields that are carried within this header. The encapsulation of data within a TCP header is referred to as a segment, since the data is generally understood to be a binary stream that is broken up or segmented prior to the encapsulation process. The TCP header itself is typically 20 bytes in size and comprises of the source and destination ports to allow the intended application to which the data is being transported to be determined. As we have shown in the previous slide, traffic destined for the HTTP service within a HTTP server will have a destination port number of 80. Delivery to the actual server is the responsibility of IP. One of the other features of TCP is sequencing. As packets are carried over the IP network, it is possible for each packet to take a varied path that may result in the packet arriving in a different order to the order at the point of transmission. It is the responsibility of the sequence number to ensure that the packet order upon delivery at the destination is maintained before the data is forwarded to the relevant application or service. The delivery of TCP segments, as with all forms of IP packet, is susceptible to packet loss as the packet in which the segment is encapsulated is carried over the network. The acknowledgement field is designed to implement reliability in the delivery of segments by returning acknowledgements each time a batch of data is delivered. The acknowledgement field is a 32-bit field that records the number of bytes received and returns a value equal to the number of recorded bytes plus 1, which is used to indicate the first byte of the next batch of data that is expected. A large number of code bits are supported by the TCP header for performing a number of operations, including the establishment, maintenance, and termination of a TCP connection. Establishment and termination often relies on the SYN and FIN bits, together with the ACK bit, which refers to the transmission of acknowledgements. The PSH or push code bit is used during the transmission of data as part of the segment to the intended destination. The URG or urgent code bit specifies when urgent notifications are to be directed to the user and is used together with the urgent pointer field. A few newer code bits also exist within the TCP header in the form of the ECE or ECN echo and CWR or congestion window reduction flags and nonsum or NS that aid in the growing implementation of applications that are sensitive to delay in order to manage congestion issues caused by heavy traffic loads on the network. The options field may often contain additional TCP parameters such as the maximum segment size value or MSS that controls the size of a segment during the encapsulation process. The options field must be a multiple of 32 bits, and where this is not the case, the field is padded with additional 0 bits to make up for the size. The window field we shall look at in more detail shortly. We firstly take a look at the process involved in the establishment of a TCP connection and the role played by the code bits in achieving this. We begin by considering that host A wishes to connect to a service that is currently operating on server A. Host A must initialize the establishment of a connection before sending any data, and does this by sending a packet carrying the TCP segment to the destination of server A. The TCP header SYN code bit has been set to 1 in order to effectively notify that host A is attempting to establish a TCP connection with the server. A sequence number that is relevant to host A is also defined, and this can begin at any value in the 32-bit range of the sequence field, giving a possible 2 to the power of 32 or close to 4.3 billion possible starting sequence values. The reception of the TCP segment containing the SYN code bit is replied to by the server. A new TCP header is created and SYN and ACK bits are set, which indicates the starting sequence number of the server and acknowledgement of the received TCP segment containing the SYN code bit from host A, which is incremented by a value equivalent to the sequence number received from host A plus 1. After receiving the TCP segment from server A, host A will return the TCP segment to server A, acknowledging that the TCP segment containing the SYN and ACK code bit values have been received. This process is commonly known as the three-way handshake, following which a connection between the two end stations will have been achieved. Following the establishment of the TCP connection, both end stations will be aware of the intent for data to be transmitted and that the received data should be acknowledged to ensure that the data is successfully delivered. We give a very simple example of this process here, in which host A transmits 3 bytes of data to the server, following which the server is expected to confirm receipt of those bytes before more bytes are transmitted. We can see that server A does this by increasing the current sequence of bytes, which in this case is 3, assuming that the current sequence number is 0, and increments this value by 1 to provide an acknowledgement number of 4. Once the acknowledgement is received by host A, the next batch of data is sent. We find, however, that 1 byte happened to be lost during transmission, and so the server is unable to acknowledge receipt of the transmitted bytes. As such, the bytes again must be transmitted by host A before the next batch of data can be successfully acknowledged. This allows all bytes to be reliably transmitted. However, where loss occurs, delay is also suffered, since host A must retransmit the lost data. In this case, we represent 3 bytes of data transmitted per batch. However, the real number of bytes transmitted before an acknowledgement is sent is determined by the window field. The window field of the TCP header is effectively a means of flow control for the data that is transmitted. This means that if too much data is transmitted between a source and destination, the window field provides a mechanism to effectively reduce how much data is sent each time before an acknowledgement is given and more data can be transmitted. In this example, the length represents the amount of data carried in a single packet, whilst the window refers to the number of bytes of data that can be accepted in a single batch by the sender. For host A, we see it is capable of accepting up to 4096 bytes of data before an acknowledgement is sent. Server A, however, is only capable of handling 2048 bytes each time. Following transmission of 2048 bytes of data from host A, server A will provide an acknowledgement with a value reflecting the total number of bytes received plus 1. Host A, upon receiving this acknowledgement, can proceed to send the next set of 2048 bytes, which again is acknowledged with a value of 4097. The window size of an end station can change as necessary, and where this occurs, the window field of the TCP segment will be updated and sent to the peer along with any data. The termination of a TCP connection after the transmission of data between the two end stations is complete relies on the use of the FIN code bit. These are sent in the sequence that is displayed here. Firstly, host A will notify server A that the connection is no longer needed by sending a TCP segment containing the FIN code bit, which server A will proceed to acknowledge. Following this, server A will generate its own TCP segment containing the FIN bit, which is then acknowledged by host A. Host A will then wait for a given period of time to ensure that the acknowledgement was received by server A based on the maximum segment lifetime timer that waits for a period equal to 2 times this MSL period before the TCP connection is closed. UDP is a protocol that provides no means of reliability or flow control mechanisms for data that is transmitted between two end stations. The true value of UDP, however, is found in its capability to support delay-sensitive traffic, such as in the case of voice and video data generated as part of telephone and video conferencing systems used over the IP network. While data encapsulated using TCP is referred to as a segment, data encapsulated in a UDP header is referred to as a datagram. The principle of a datagram refers to the capability of data to be transmitted between two endpoints without prior communication. The same principles apply to the IP packet, and therefore IP packets may also at times be referred to as a form of datagram. The minimalist approach taken by UDP means that data is not guaranteed to reach its destination, since no connection exists between the two communicating end stations to support acknowledgements. If we take a closer look at the UDP datagram header as part of an IP packet, we notice that the number of fields supported are significantly less than those carried by TCP. We find that there is no means of sequencing, no means for acknowledgement, no flow control mechanisms such as the window field of TCP, and no code bits to support the establishment and maintenance of a connection. UDP simplifies this entire process by providing fields for only the source and destination ports, the length field for detecting size discrepancies, and the checksum field that is found in all protocols seen up until now that ensures that should the integrity of the header be affected, that the receiving host UDP can detect the problem and discard the datagram. This means that UDP will only use 8 bytes of the total 1500 bytes of the packet size and thereby allow more data to be carried per packet than compared with TCP. The transmission of UDP is open to a number of issues that are prevented through the use of TCP, such as the potential for datagrams to be duplicated and arrive at the destination out of sequence, generally as a result of traffic's capability to traverse multiple paths in order to reach the destination. One of the key factors of UDP is its suitability to traffic that is considered sensitive to delay, such as that of voice and video data. The reason being is that UDP has no requirement for acknowledgements to be sent each time a batch of data is received at the destination, and so the delay involved as a result of waiting for an acknowledgement is non-existent. Another reason lies in the case of data loss during transmission. In the case that some packets are unable to reach the intended destination, TCP would generally require that these packets be retransmitted, which again would lead to extensive delay and cause major call and video quality issues over the network. In the case of delay-sensitive data, it is in fact better to consider the data lost and avoid retransmission. This would cause some slight disruption to the transmission, however would provide a better overall service, since the service would still be perceived to be functioning in real time. In summary of this section on transport layer protocols, we ask a couple of questions here. The first is, what is the purpose of the acknowledgement field in the TCP header? Well, this acknowledgement field in the TCP header enables the segment received by the TCP process to be confirmed. This effectively enables reliability of transmissions, since any packets sent that are not acknowledged can be resent. Finally then, we ask, which TCP code bits are involved in the TCP three-way handshake? Well, the three-way handshake uses the SYN and ACK code bits to establish the connection between a specific application or service of both the sender and receiver, following which IP packets can then be forwarded between the end stations to support the application-to-application transport of data.